we talked about with biology how it's a lot of it is just kind of stacks of copies on top of one another over and over again, and we've also talked about how kind of in the standard model it's difficult to take all of these fundamental ideas and say, I don't know, lead collisions isn't going to be easily predicted by the standard model. It's a much more emergent behavior. Do you think that there's something kind of that these two could grow together? I know there's been a rise in computational physics theories where you have this idea of taking multiple stacks and stacks of some kind of simple rule or some kind of basic physics principle, and then using that as a kind of way to build up a final theory or unified theory.
Well, it's conceivable, I guess, that we'll have a final theory that looks very, very different from the kinds of theories that have been so successful in physics so far. Things like that have happened in the past, of course. We had extraordinarily successful framework from Newton of particles and forces between particles that was, predicted many, many things quantitatively with extreme success, but then started to show seams in the 19th century and gave way to field theory, which has introduced a host of new ideas, none of which were, I would say, in conflict with the Newtonian framework, but certainly required additions. And that was very successful, electromagnetism and everything. But then that got replaced by quite a different theory that's really profoundly different. I mean, well, first of all, there's the relativity theories, which I would say are not profoundly different. They really are in the spirit of field theory of electromagnetism. They introduce a host of new ideas, but I wouldn't say they required to unlearn anything really. Whereas quantum mechanics really was very profoundly different. And it's amazing that you can have such a successful theory as pre-quantum physics that explains so much that is profoundly misguided in some sense, right? As the real story, when you go one level deeper, is quite different, and in fact, it's a very challenging problem that people are still working on to show how classical physics and the classical world emerges from the quantum world, which we think is more accurate. And so based on all that, it's conceivable to me that the present formulation of physics, which is based on continuum, space-time, and real numbers and quantum fields and all this stuff, that would be replaced by something different, something that's more digital, like a cellular automata or something. It's conceivable, but boy, it's a tough thing to. Let me put it this way: it's not conceivable by me. I don't know how to do that. I played with it, tried to give it a chance, but it's just, it doesn't. It's not easy because even to do basic things like implement conservation laws, implement symmetries, which are have been profoundly fruitful guiding principles in getting to our understanding of physics and are embedded in our best models of the world. You have to sweat blood and tears to get them, and it looks very ugly to implement them in these other frameworks. So seems tough. but there might be but like in the case of quantum mechanics, it didn't discard classical physics. It you still have P's and Q's, momenta and positions, but they just don't commute. So, well, you have but you also have a different framework. You have Hilbert space, and if a sufficiently profound modification might involve a synthesis of different ideas. So, for instance, I mean, specifically, an idea I have a lot of sympathy for is that there's an atomic structure to space-time, that space-time itself is made out of some kind of particle, roughly speaking. But then you have to say, what are the laws for those particles? And I think those laws, I think, it's very hard for me to imagine that they will resemble the laws of simple computer programs for cellular automata. They're to me, much more likely to obey a different set of ideas that are more related to quantum mechanics as we know it.